The magnetic potential is an alteration of space around a moving charged particle or an electric current. The magnetic potential is a vector field, which means it has a magnitude and a direction at every point in space. This is different from the gravitational and electric potentials, both of which are scalar fields. Finally, the units of magnetic potential are joules per amp meter. This is the equation for the magnetic potential of a moving charged point particle. It depends upon the net electric charge of the point particle, the velocity of the point particle, and the distance from the point particle to the position where the magnetic potential is measured. As with the equations for the magnetic field, the equation for the infinitesimal bit of magnetic potential of an infinitesimal bit of a current carrying wire can be derived from the equation for the magnetic potential of a moving charged point particle. This is the equation for the infinitesimal bit of magnetic potential for an infinitesimal bit of a current carrying wire. We see that it depends upon the current in the wire, the infinitesimal bit of length of the wire, and the distance from the infinitesimal bit of wire to the position where the magnetic potential is measured. Recall that the vector ds points in the direction of the current. It is clear from these equations that the direction of the magnetic potential vector is the same as the direction of the velocity of a positively charged point particle, or the direction of the current in a wire. The magnitude of the magnetic potential vector decreases as the distance from the particle or the current increases. Magnetic potential energy is energy that exists because of the interaction between two magnetic objects, such as moving charged point particles or currents. Magnetic potential energy can be considered to arise from the interaction of one magnetic object with the magnetic potential of the other magnetic object. This is the equation for the magnetic potential energy of a moving charged point particle in an external magnetic potential. It depends upon the net electric charge of the point particle, the velocity of the point particle, and the magnetic potential through which the point particle moves. We can use this equation to determine the magnetic potential energy of a 2 nanocoulomb charge moving with this velocity through this magnetic potential. Substitution into the equation for the magnetic potential energy gives us this expression. We can expand this expression into 4 different dot product terms. 3 of these dot products are 0. Thus, the magnetic potential energy of the system is 1.2 nanojoules. This is the equation for the infinitesimal bit of magnetic potential energy of an infinitesimal bit of current carrying wire in an external magnetic potential. It depends upon the current in the wire, the infinitesimal bit of length of the wire, and the external magnetic potential. Recall that the vector ds points in the direction of the current. We can use this equation to determine the magnetic potential energy of this current carrying wire in this magnetic potential. The total magnetic potential energy of the system is found by integrating the infinitesimal bits of magnetic potential energy from each infinitesimal bit of length of the wire. Since the current is constant in the wire, it can be taken outside the integral. The vector ds points in the positive z-axis direction and has a magnitude dz. Substitution of these variables into the equation for the magnetic potential energy gives us the following expression. Only the z-axis component survives the dot product. The resulting integral is along the z-axis of the wire and is equal to the length of the wire. Substitution thus gives us the following expression, and a final answer of 2 joules for the magnetic potential energy of this system.